So far I've asked you guys to do the 1 through 40 for the homework check on Sunday. And we've assigned 41 to 48 for this week already. Before we start getting into the new things, are there questions from any of that we want to address before we start the new things? Luke. Sure. So 21. So on all of 11 through 28, that's the same directions to eliminate the parameter and find the domain and range for the resultant function. So for 21, to eliminate the parameter, you could start with either the x or the y. Traditionally, we kind of start with the x equation, but it doesn't really matter. And maybe in a way for 21, it might be easier to start with the y because it's a linear function, but then you have some rearranging to do it. Oh, it's whatever. I'm going to start with the x anyway, so I'm going to just start by getting the t by itself. So add 1 to both sides. Multiply by -2. Square root both sides. Notice that because I'm square rooting both sides, it's generating the plus or minus there on the square root. Now, I'm not going to worry about the -2 that's underneath the radical here. Why don't I have to worry about that? Because I have a variable along with it, right? Like if the x is -5, then I have a positive number under there, and it's not a big deal. So this isn't automatically a ridiculous statement that I've written. Everybody's okay still? Okay. So I'll plug this in for t into the y statement now. Maybe I'll just write it the same way. So I have 2 times plus or minus -2 square root of x plus 1. And, well, I guess we'll just multiply the 2 in, so it's like 2 plus or minus. And as far as I'm concerned, that's a fine answer. I think the answer in the back of the book is a little bit different. What is it? It's like it's -8x minus 8 or something under there, which is the same thing. It just rearranged or whatever. But either would be fine. Like what? It's not a big deal. Like right is right, you know what I mean? Like now you're talking about just like a question of preference. We still have to talk about the domain and range part. So to get the domain for this function now, I'm going to consider my parametric equation for x. Which is -1/2 t squared minus 1. And the t's on 21 are defined from -infinity to +infinity. So because this is a quadratic function, and because I know that quadratic function opens down, I know the output for this function is going to be -infinity up to whatever the y-coordinate of the vertex is. Oops. Right, I know it's going to look like this. The question is just finding the y-coordinate of the vertex. So to find the vertex, that's -b over 2 times a. So the t coordinate for the vertex is 0. And then when I plug 0 in, I just get -1. So there's my range, or my output for my x of t function, which is the domain for my Cartesian function. The range is really easy. So my range is a linear function. And the input for that linear function is all real numbers. Oops, I meant x here, not y. So that just means that the range for that linear function is also all real numbers. Does that feel okay, Luke? Jake? For x of t? So this is a t x of t plot. So we're going to have, like, here's the vertex at 0, 1. So the graph's going to just look like that. Well, the output of x of t is the domain for y equals plus or minus 2 square root, yada, yada. Which makes sense, right? Because if I take something from here, that's a negative number, right? That's less than 1. If I plug negative 2 in for this, I get a negative times that negative is a positive, so I'm square rooting a positive, which is good. If I picked like 0 or something, 0 plus 1 is 1 times negative 2 is negative 2, and then I'm square rooting a negative, which I know bad things.
So if it was on a regular plot, they would be flipped.
So if it was on a regular...
If the x-axis was horizontal and the y-axis was
if the... what is it?
the domain and range would be flipped.
So if we were talking, those are the domain and range for this.
Oh.
So we're using the parametric equations to determine the domain and range for the Cartesian function.
That's not the domain and range of what?
Exactly.
Okay, that makes sense.
Okay. Yeah, and this is what makes this a little bit tricky, right? As you're stepping through, you have all these different kind of like pieces that are in themselves functions, but are contributing to different parts of the piece that we care about, which is the Cartesian version of this parametric function.
And I could put in the square root of ax, whatever it is. That makes sense.
Yes, yeah. If you looked at your calculator, the graph of that's going to, be something like, like this or something. Actually, I think it'd be, because it's plus or minus, it would have two sides to it, which I think supports what we're seeing over here, right? And in fact, that should be negative 1, 0. Would be that point at the end. Okay. Others. This was a good discussion, though, right? Making sure we're clear on like the vocabulary and kind of what parts are telling us what information. Jacob, you go.
Did you see the range?
The range for 12? Yeah, man. So for the range, all I care about is the y of t function, which is t plus 2. And we're told the input for that y function, well, I should say the parametric equation for I, let's use the most precise vocabulary I can, so try and make it less confusing, is negative 3 to negative 1. Since this is a linear function, all I need are the endpoints, because this is representing a line segment, because its input is fixed, right? It's not unbounded. So I just need to do y of negative 3. And then I just need to do y of negative 1. So then I have my range goes from negative 1 to positive 1. Does that feel good? Oh, well, you just do the same thing with the x function.
Yeah, no, I just want to make sure.
Oh, so it'd be like, what would it be? 8 to 14 or something? Okay. Yeah, no problem. John, did you have something too? 26? Okay. So all of the 25 through 28, you're going to do differently than what we did the other ones, since those are the ones with the sines and cosines in it. So here, what we'd want to do is we'd want to sketch a picture. When you sketch the picture, you're going to notice that's a circle. When I say sketch a picture, I mean just use your calculator, whose radius is 3 and the center is 0, 0. Yeah, of course. Yeah. So from that, we know that the equation for a circle is going to look like this. So that would be our our Cartesian. We should check this using our parametrics now, though. So I have -3 cosine t was my x function or equation, and then -3 sine t was my y equation. And we want to see if that does indeed equal 3 squared. So when I square those, the negatives go away. And I have 9 cosine squared t plus 9 sine squared t if I factor the 9 off. And I notice that cosine squared plus sine squared is just 1. And 9 times 1 is definitely 3 squared, so we're good there. And then for the domain and range, there's not really anything to do since it's a circle with radius 3. I know just the domain and range both go from -3 to +3. Is that?
Yeah, because I tried doing it like the rest of them.
Yeah, and it gets a mess when you try to like eliminate the parameter because you have the inverse inside. Yeah, it's a big mess.
Yeah.
So just to recognize that if I have like sine and cosine of stuff, it's a circle, man. Well, if the two radii are different, then like maybe you end up with an ellipse or something, but we're not dealing with that in this course. Taylor.
Or can I ask about like 41 through 48?
Heck yeah.
42.
Sure. So 42 says a ball is thrown straight up in the air. One-dimensional motion. Right? Because we're going straight up. So that's the first critical thing in that story problem is making sure you're using the right parametric function. Could you use the 2D one? Sure, if you fix the x position to 0 or something, or 1 or whatever, so it's constant. You could do that still. From an initial height of 5 feet with an initial velocity of 80 feet per second, write an equation to model the height y of the ball as a function of time. How high is the ball after 3 seconds, and then what is the maximum height? Okay. So again, I'm using the two-dimensional motion problem. So it's -16t squared plus the initial velocity times t plus the initial height. Part B is we're just plugging 3 into that. Whatever. I'm going to let you handle the plugging in. Is that cool, Tay?
Yeah, it was just the last bit.
Oh, okay. So for this piece, this shape is a parabola, right? It'll look like this or something. So the maximum height is the y-coordinate of the vertex.
So this we just plug in.
Oh, I mean, you could also do, -b over 2 times a, right? So that gives you something, and then you can do y of whatever that number is and just find it precisely. Or you could use the maximum minimum command on your calculator. That's not unreasonable either.
I think I was just doing the wrong dimension.
Yeah, if you tried to do 2D motion, that makes this kind of a pain in the tuchus. John.
Quick clarification. So when we do the calculation for the vertex, our y coordinate is y of x.
Mhm.
Are we using the like the original equation, like -16,
Yeah.
but x is t?
Well, I used all t's everywhere in here, right?
Yeah,
I wrote t, t, t. So this is like a yt plot that I drew here. But that's describing the height versus time, which is typically the way you would graph something like this, not actually modeling the motion of the ball, which is just this, not a...
So the vertex are max height or the time in which the max height is reached?
So the question says, what is the maximum height of the ball? How many seconds does it take to reach that maximum height?
Oh, it's x height and y.
So this is t, comma, y is a point here. So the time is the x coordinate. That's how long it takes to get to the maximum height. The y is the y coordinate. That's the actual height. I would have preferred to use the letter h there instead of y, because I think it makes it a little bit clear what's going on, but the direction said specifically y feet, so it wanted you to make a y of t function. But what, like, we're talking about alphabets here. The letters mean whatever we want them to mean. It's just we've double used so many of them, it gets confusing, right? Does that feel okay?
Yeah.
Okay. Tay, you're good? Okay. Anybody else have questions here from the H-dubs before we move on? Okie dokies. That's cool. Let's get on with our bad selves here. We're going to go to section 10.3. We're going to transition from talking about parametric things to polar things. And what we're going to talk about first is just the polar coordinate system. So up until this point, everything that you've graphed has been using the Cartesian or rectangular coordinate system, where you're plotting x's and y's. Everybody okay with that? Even previously, when we were graphing the parametric functions, what you were plotting were x and y's, right? There's no t coordinate anywhere going on inside those when we graph the actual parametric function. We're still just plotting x and y's. We're using the t to generate the x and y coordinate, but when we actually graph the parametric function itself, the t doesn't appear anywhere in there. So it's still just a Cartesian plot, even though it's from a parametric function. Is everybody okay with that? What we're going to do today is we're going to define an entirely new coordinate system called the polar coordinate system, and we're going to start with that definition. I'm going to abbreviate polar coordinate system as just PCS from here on out because that's a lot of letters to write, and I don't like writing things down. And that polar coordinate system, or a point in the polar coordinate system, is defined by the general form r comma theta, where r is the distance from the origin to the point, and theta is the measure of the standard position angle whose terminal side intersects the point. And I just want to change one little article. Instead of that saying the standard position angle, I'm going to put a standard position angle. And that just matters to the math grammarians out there. Okay, so what are we really saying here? It's easier with a picture. You'll notice in the content library I have a page here called Polar Graph Paper. I'm going to use that now and just drop it into the notes. We'll show you what the polar coordinate system really looks like here. I put this in the content library, so as you're graphing polar points or graphing polar functions, you have polar graph paper that you have access to. Feel free to use that as many times as you need in the course of doing your assignments. That's what it's there for. Okay, so when you look at this polar coordinate graph paper, it's not a spider web, it's not a bullseye, it's not a dartboard. This is the polar coordinate system. The circles that you're seeing are all circles of differing radii or differing radius. So the first circle is when the radius is 1. That's when r is 1. And then r equals 2, 3, 4, 5, 6, 7. I guess that last little tiny bit would be 8. Everybody's cool with that? The straight lines are representing angle measures. And the increment we're going up by is 30 degrees, which is pi over 6 in radians. So that's pi over 6. This is 2 pi over 6. That just reduces to pi over 3. And then 3 pi over 6, which is pi over 2. And at this point, I'm going to stop writing the angle measures because you guys can probably count by 30s pretty well. I'm just going to write the radian measures because it's a little harder to do that, I guess. I mean, that's insulting to you guys. It'd be like, hey, it's not that hard, Mr. Kulik. And I'd be like, you're right. It's not. But I'm still going to do it because, I don't know, sometimes fractions freak people out. You know what I mean? We're just going up by sixths and reducing things. But it's been a minute since we've done this, so like there's no harm in just doing it again. And now I've lost count. I think we're at 10 pi over 6, and then 11 pi over 6, and then back to 2 pi or whatever. That's right. Everybody's okay with that? So again, each of the straight lines is a sixth of pi or 30 degrees. No big deal. Let's plot some examples now. So let's say we want to plot the point 3, 120. When I'm doing this, I like to start with the angle measure. So where were we? We're 30, 60, 90, 120 is there. So I know I'm going to be on that straight line. And then the 3, I'm just going to count from the origin, 1 to third circle. So that's my point. Pretty easy, right? Not a big deal. Let's do another example. Actually, let's just do it over here. All those angle measures that I drew on the previous, or the circle, or the grid above that were kind of cramping my style there, and I just need to get rid of them. Okay, so same thing. I'm going to start with the angle. So we have pi over 6, and then 2 pi over 6, which is pi over 3. So we're talking about that line. But notice that it's a negative 2 here. So what's that negative sign on the radius going to mean? Means that we're actually looking at the other side of that straight line. And then we're just counting 2. Gonna count 2 circles out, so my point would be there. Does that feel okay? Do one more. So let's say we want to plot -1, -100. Again, I like to start with the angle first. Notice that angle is negative. What does that mean? We're going the other direction, or you could add 360 to it and find a coterminal angle. That's kind of the way I prefer to think about it. So I know 240s here and 270s here. So 260s like over here somewhere or whatever. Maybe I can draw that a little straighter. Nope, I can't. One more try. I'm a failure. So there's the 260. But remember, I have a negative here on my radius, so really I'm talking about that part of it. Was that any straighter? Not really, I guess. And then we're looking at 1, so we're talking right there. What's the takeaway on this piece? The negative side on the angle doesn't flip anything, right? It's only the negative sign on the radius that you do the flip. Flip it for real. Anybody have anything any observation you want to make? Anything that's different about these polar points than Cartesian points? There is a big difference. Something that can happen with polar points that can never happen with Cartesian points. Let's go back to the second example here. Is there another way I could describe this location? Couldn't I use +2 and then this angle? That's going to describe the same location, right? Is that the only other way I could describe that location? No. How else could I use? Okay, how? How infinite? Oh, coterminal angles, right. Yeah. So I could use +2 and then anything coterminal to that angle in red I've drawn. Or I could use -2 and anything coterminal to pi/3. Everybody agree with that? So unlike Cartesian points, where each location is described uniquely, there are no unique locations in polar coordinate points. There's infinitely many ways you can describe a specific location. Let's formalize the observation we just made here into a definition. So let's say we have some point P that's r comma theta in the polar coordinate system. Bless you. Okay. So any point corresponding to the same location must be of the form we had mentioned there that there's going to be two forms, right, that we could have. So one of them would be everything coterminal to the angle in the first point, where the radius stays the same. Or if the radius is negative, we'd have to flip the side of the angle we're using, and then consider everything coterminal to that one. And then obviously if you were talking about angles that were measured in degrees, you could likewise write the same thing and replace the 2 pi's with 360s and the pi's with 180s. But that's the only way, right? There's infinitely many ways to describe a location, but there's kind of only 2 ways to generate those infinitely many, right? All right, let's say we're asked to find all the polar coordinate points that coincide with 8, 5 pi over 6. When we say coincide, what do we mean? Yeah, they occupy the same location, right? So all we need to do is use our criteria from above. So we'll take everything that's coterminal to the angle and the point. And we have everything that's got the opposite signed radius, where we flipped onto the other side of that line, and then coterminal to that. Notice here that we could combine the like terms here. And really, this would be 11 pi over 6. That looks a little bit 2-ish. That looks a lot less 2-y. Everybody's cool with that? Pi is 6 pi over 6. When you make a common denominator and you add the fractions, you add the tops, bottom stays the same. But that's really easy, right? There's a little formula. There's nothing tricky about it. Mr. Kulik, can it get trickier than that? Well, nah, man. Like, doesn't get trickier than that. Well, let's do one more just to make sure. What's different about this one than the previous one? It's in degrees instead of radians, but like, what did he do, Mr. Kulik? So everything coterminal to the angle in the original. And then we also have the things that are of opposite signed radius that are flipped across the angle line and then coterminal to that. And again, just like we mentioned before, oh, I thought I picked the color. Before, we can combine those like terms. And really, that's negative 54. John.
Combine them, let's say, plus or minus r, beta, plus or minus c, 5 plus or minus 5. Okay.
I don't think so. I don't think that works. because these two are not always going to be. I think the way you're describing that, I can get things that are not actually in the same location. Like you can get something that's in one of the other quadrants. Say it again. Let's just double check.
Plus or minus r theta plus parentheses
Okay, so we have plus or minus r comma theta
plus parentheses 1.5 plus or minus
0.5
1.5
One-
because then you get the 1 pi k
plus or minus 1.5.
plus or minus 0.5 right? Close parentheses pi k.
IK. Okay. So what happens if
Well,
k is equal to 4? In which case that would be theta plus 0.5 pi. And that's not one of the ones that you want.
what if you put the parentheses after?
So you want to move this to there
That before the pi.
before. I see. You want it here. Well, isn't that? I see. Okay. So that is just going to be either pi, right? Or 2 pi. But the problem is that you have pi times k. So if it's just pi k and k is equal to 3, you'd have like theta plus 3 pi. You know what I mean? Like I don't think you can kind of combine this all into one and have it always work out. You know what I mean?
Yeah.
But I mean, if there was a better way to combine it all together, like we're mathematicians, like can we find a denser way to write this that uses more notation that like allows me to use one line instead of 2 lines? We're definitely always interested in that because why? Mathematicians are lazy. I prefer to say it as efficient. That's the generous way of doing it. The ungenerous way would be calling us lazy because we don't want to write anything down. Okay, so we have this new polar coordinate point system, right? We've described how to plot these points and like observe that there is this weird thing in polar coordinates where we have lots of points that are all describing the same location, but that's fine. What do you suppose we do next? We know how to plot things in polar points, and we know how to plot things, or we know how to plot polar points, and we know how to plot Cartesian points. Yeah, we want to go talk about how we go back and forth, right? And I can't remember how interchangeably, but we use these in the notes or the homeworks, but the terms rectangular coordinate system and Cartesian coordinate system mean the same thing. You can use those two terms interchangeably. We're probably inconsistent in the directions. I don't want to, in some of the homework problems or in the notes or whatever, I don't want to mess anybody up there, but it's probably worth just pointing out that those two terms we're going to use interchangeably in case I do. I try to use the word Cartesian because that's what we called it when I was in your shoes when I learned this the first time, but rectangular is used in some areas also. So anyways, so this is actually pretty easy. To go from polar to Cartesian, we need to generate an x point and a y point. The x point is just r cosine theta. The y point is just r sine theta. If you think about that, so we had like this guy here. That looks exactly like a problem we did before, right? The length of the sides of that triangle are going to be r sine theta and r cosine theta. Woohoo! Right? That's pretty righteous when this folds back onto something we did first semester. You might have also recognized that this is just one of our definitions for sine and cosine rearranged a little bit. In first semester, we said cosine was x over r and sine was y over r. That's just rearrangement of those two formulas. Cool. To go from Cartesian points back to rectangular, from Cartesian back to polar is a little bit less clear, but since we're talking about the distance to the origin just being r, I can use the distance formula, and when one of the points is the origin, 0, 0, it just turns into the Pythagorean theorem. Oh, okay. And then I'm going to use the fact that I know tan theta is y over x. I'll put a little asterisk by that because that's not exactly how we're using that, because that's not exactly what theta is. But, you know. And now it's just time for a couple of examples. So let's say I want to take the polar point -3, 148, and convert that into the Cartesian form. Well, all I need to do is -3 cosine 148, -3 sine 148. Turning on my calculator, I want to check to make sure I'm in degree mode, which I am, but it does not matter if your calculator is in function, parametric, or polar mode. Unless you're using the graphing features, that part won't matter. If you're just doing like sine and cosine or whatever, it doesn't matter. All right, so -3 cosine 148 is 254. And -3 sine 148 is -159. Whoa, Mr. Kulik, you haven't even pressed enter yet. How do you know that? I've done this problem like 4 times now. So you just remember after a while. So when we put this together, there's my point. John? Of course. Mr. Kulik, does it get harder than that? Nah, man. Just plug it into formula. Okay. Next one. Let's say we take the rectangular point and want to change that in -3, 2 and change that to polar. It was a little bit more challenging, but only marginally so. So I'm going to start by figuring out r. So r could be plus or minus 13. So you have a choice, right? Because I know that I can write a polar coordinate lots of different ways. Which way do you suppose Mr. Kulik suggests you use? The positive square root 13 or the negative square root 13? Yeah, why the positive one? Because you don't have to do the flippy flop, right? We have to remember to account for that, which is kind of a pain in the tuchus. So I would always choose square root 13. Could you do this with the negative? Sure. Does it make the problem harder? Absolutely. Would you ever want to use the negative? No. But you could. I don't know a good reason why you'd want to, but other than just like, that's what I decided to do this time. Anyways, there we go with that. Now to get the theta, we have the point -3, 2, like over here. So when we talk about theta, we're really talking about that angle, correct? So this is like my alpha's down here. The other side of the reference triangle is 180. So theta in this case is going to equal 180 minus alpha, where alpha is the tan inverse of the absolute value y over x. Oh my gosh, Mr. Kulik, is this looking familiar? You better hope so. We've done this thing about 4 times. We've used the same process to do a couple of different kinds of problems, right? Hopefully you're getting pretty good at this by now. So it's calculator time for me. So 180 minus tan inverse, and then the absolute value of negative, or of 2 over negative 3. I'm not going to bother with the absolute value. I'm just going to do it on my calculator, make it tan inverse of positive 2/3. And I get 146.3 as my alpha. Or I'm sorry, my whole theta. My apologies, I did the whole thing there. So one possible answer could be this, right? That's a point that works. That's the obvious one. That's the one I would always give. Is that the only answer you could give to make it correct? No, right? Anything coterminal 146 with square root 13 would be fine. Or if you did negative square root 13 with, what is it, that 326.3 would be fine, or anything coterminal to 326.3 would be okay also. I mean, the question here would be why would you ever do that? But, you know, maybe you're just feeling funky that day and it's like, let's get crazy. This feels like a good place to stop here. That closes section 10.3. Which is pretty good, right? That was a pretty easy guy.